2, 1. So organized counting, additive counting principle. Now, when you're going to be doing organized counting, you typically ask yourself the question, how many outcomes, do we have from a particular situation? And it is a very popular thing to start with when you're beginning probability. You do organized counting actually all the way probably back in elementary school, and then it kind of creeps back on you if you do probability. It's not always very easy to be able to count these things. They seem simple when somebody shows you, but you run into examples where it's not as simple. Now, I've done the first original video on organized counting, which was for the multiplicative counting principle, when you would be multiplying certain things based on the outcomes that can happen. And I'll put up a link up above there because you do have to know that if you're going to be watching this video. So now, what is this additive counting principle, and how does it differ from the other video that we have done? Well, when you're going to be counting and you run into this situation where you have mutually exclusive things occurring, typically we'll say them events or something like that. Now, mutually exclusive means that two events can't happen simultaneously at the same time. Okay? So let me show that to you through an example. So let's say we take this set. So this set has a triangle, right? Has a circle and a square. And maybe, we would want to be able to take this set and then create some patterns, right? That we would have. And maybe those patterns would be a representation. They would be some kind of a signal, right? That we would be sending and somebody else would decode it. So if we send a triangle, it would mean something. If we send a circle, it would mean something different. If we would send a square, again, it would mean something different. And also, maybe we can combine them. We can send a circle and a square together, right? So it would be two symbols at a time. So let's imagine that we can send, either one, okay, of these figures, two of the figures, or maybe even three of the figures, okay? So as you can see, if you're going to be sending one figure, simultaneously you're incapable of sending two figures, okay, at the same time, because that other person receiving it is going to be waiting for something to come in, and they're coming in one at a time. So how many of these outcomes would we have? Well, it's pretty easy, right? So if I have this, I'm going to take, okay, and let's say this is my triangle, this is my circle, and this is my square. So I'll put letters on them. So if I was only sending one item, it would have given me, I would have had three things to choose from. It would have been either I would send a T, or I would send, okay, just a circle, or I would send a square. So I would have three outcomes that could be possible that the person on the other hand would be receiving. Now, if I would send two at the same time, then what could happen is I could send maybe a triangle and then maybe a circle, right? I can do that. Maybe a triangle and then maybe a square. I can certainly do that, right? Then I can send, for instance, maybe a circle, okay, and then a triangle. So that would be a little bit different, okay? So the order matters here. I could send, a circle and then a square. And then I can continue this. And then I can send, okay, so maybe a square and a triangle, and then a square and a circle. So I have 6 outcomes here, right? That's what I would have. And now, notice you can't simultaneously have one item that you're going to send, okay, and then at the same time send 2 items. So they can't happen at the same time. So these symbols, right, you either send one, or you're going to send 2, and maybe there's some meaning behind this. Now, in total now I have 3 outcomes if I would send only one item. I have 6 outcomes, right, if I would send 2 items. And now if I did this for 3 of them, now instead of doing all the possible combinations, So if I had 3 of these items, okay, what I would do is, okay, so I'm going to be sending, okay, some kind of a signal with these 3 items in there. And I can actually use the multiplicative principle, right, to have here. So what would happen? Well, okay, so if I would do this, okay, so then that means that on the first go, right, so I can have, so either on the first one I can have a T, which is a triangle, a circle, okay, or a square. That's what I can do there, right? Okay, so now if I send a triangle, okay, so within here, so it would have been a triangle, okay, maybe a circle, and then a square. So it could be one symbol out of that. Now I can also send a triangle, and then I can flip-flop. I can have a square and a circle. But I can't really do anything else, right, that's any different here. Okay? And now I can do the same thing. I can put a circle first, okay, and so on. Now, instead of doing all these combinations with these 3, then instead, as I said, I can do the multiplicative, okay, principle, which says, well, I have 3 choices, okay, in the beginning. I have either a triangle, a circle, right, or a square. Now, if I'm going to simultaneously, right, now choose, okay, on the next one, because I've chose one of them already, whichever one it was, it will leave me only with 2 choices. It's kind of like picking those cards, if you remember, from that multiplicative video, right? If you choose a card, right, then, and you keep it, well, then you have less cards to choose on your second pick. So now that's the same thing. And then lastly, what we would have is we would only have 1 choice for the last thing, because if I picked 1 for the first, picked 1 for the second, so now 2 are gone, and that only leaves me with 1. And now by the multiplicative principle, if I multiply this gives me 6 outcomes as well. So I would have 6 outcomes right there. And now what you see is, okay, you see 3 outcomes if you only send 1 of these figures, okay? 6 outcomes if you send 2. And then, okay, you have another 6 if you send 3. So in total, I can add them up, right? So I would have in total 15 possible outcomes, okay, that I could send out to the other line. And now this is what the additive counting principle is all about. So if things cannot happen simultaneously, meaning I can't send 1, okay, at the same time as I send 2, then what you do is you would count them individually, and then you start adding them up. And the addition is the additive counting principle. So that's what would happen within here. So the additive counting principle, what it states is, if you have mutually exclusive events that they cannot happen at the same time. So at stage 1, okay, so in this case it was just sending 1 item, and you have, let's say, n of those. So you would have in stage 1, you would have n, okay, in stage 1. You count all of the outcomes up, and then you have n2 outcomes in stage 2, okay, and so on. So you would have this continuously. Then the total number of outcomes is the summation of all of them. That's what the additive counting principle is all about. The multiplicative counting principle was when we were multiplying, because we were trying to see. So like we did right here, where we were basically multiplying these through. You had 3 possibilities for the first, 2 possibilities left for the second, okay, and then 1 possibility at the end. So we weren't assuming that we were putting things back. And that was the multiplicative because we were multiplying. Now I could have done this for here. I didn't have to list all of these out, right? So I had 3, okay, and then 2, right? So I had 3 choices for my first, right? 1, 2, 3. And then it would only leave me 2 choices for the second. Okay, and if you multiply this, you would get your 6 outcomes like we have drawn them out, okay, on the left-hand side. But the additive principle is, okay, you can add all of the outcomes together like we did in this case. Now, where else is this applicable, right? Like, where can we see this? So here's another example that I'm going to show you where you can use this additive counting principle. How about passwords? Well, we have all kinds of passwords. And to be honest with you, here it says, we're going to be creating a password with minimum 3 characters or a maximum of 5 characters, right? Most passwords now are going to have probably a lot more than that because it's so easy to crack them. Okay, but let's stick to this and let's see how could we possibly count the total number of outcomes. Okay, so let's take a look, and we're going to try to apply these multiplicative and additive counting principles to do these. So I'm going to do part A first. So characters, okay, are only letters. So let's assume that they're only letters. Are they either small or capital? And we're going to assume that it's the English alphabet, right, which is 26 letters. So I'm going to make the assumption A. So I have 26, okay, of the small ones. And then if I capitalize them, I have another 26. So that's the capital ones. So in total, I have 52 possibilities. All right. So now let's see this. Now it says my password's supposed to be a minimum of 3, but a maximum of 5. Now they can't happen simultaneously, right? You can only have one password. So the password either has 3, 4, or 5 characters. But you can't have 2 multiple passwords, let's say, for the same exact thing. So that's what we mean. So these are now going to be mutually exclusive. You can either have 3 characters, you can either have 4 characters, or you can either have 5 characters. And we're going to be adding them up, right? The total number of outcomes that we get from 3 characters. Now, how can I do that? I'm going to use the multiplicative. So for 3 characters, right, that I have right here, it doesn't say that this is restricted. So we're going to be kind of taking 52, right? So I have 52 choices, either small or capital. Now I'm not removing one of those choices, right? At least in this password, so they're not restricting us. So now on the next pick, okay, I also have, so for my second letter, in this case, I would also have 52 choices. And then on my third one, I would also have 52 choices. And I'm going to be multiplying this. This is if my password was 3 characters, in this case 3 letters, right? And I can get exactly what the total is. Now it's going to be a pretty big number. So 52 times 52 times 52. So we have 140,608 possible outcomes here. It's quite a bit, right? If you include all the letters, both small and large, it's quite a lot. Now, the second thing is, what I would do is, I got to find all the possible outcomes from 4 characters. So this would have been 1, 2, 3, now 4, right? Now, it's no different. I'm going to have 52, 52, 52, or 52. Okay, so now I have all of these choices, which is a little crazy. Okay, so I already did it 3 times, so I'm going to take this answer and then multiply it by 52 again. And notice that, this thing just starts to balloon. So 7,311,606. That's how many outcomes that I would have for 4-letter passwords. Now, it says a maximum of 5. Okay, well, if I did that, so if I did now 5, so this would have been 52. You can see the pattern here, right? So I would have had 5 of these. So this is 52 to the 5. And if I would do that, I'm going to just clear this out. 52 to the 5. It's monstrous, right? So this now all of a sudden starts to really balloon on us. This is what we have. So you can imagine, sometimes now our passwords, they're telling us we have to have at least 8, and it's not just letters. It's probably with characters, with symbols, and all kinds of other stuff. So there's so many possibilities. Now, but because the computers are now so quick, these hackers can hack them pretty quickly. They can go through a lot of these passwords rather quickly and then check them. So nowadays, we don't have just passwords, they'll do other additional second step, either questions or maybe they'll send you a text and you got to verify a code, all kinds of stuff to try to protect us. So now I have all of these. So in total, I would have to use the additive principle in between them. And that additive principle would say, okay, so how many total ones do I have? Sorry, okay, so I have all of these. So I have to add these up. Okay, so I'm going to clear this. Okay, and it would have been, so I'll do it all from scratch. So 52 to the power of 3. Okay, so that was this one. And then plus, okay, now the second one, which was 52 to the power of 4. And then plus 52 to the power of 5. And, you know, as you can see, the one that has 5 dominates, but the other ones also add some possible outcomes. It's quite a lot of outcomes that we would have from something like this. So I've used the multiplicative for each stage, but since each stage, each password between 3 and 4 and 5 can't happen simultaneously, can't have a password with 3 letters and at the same time with 5 letters, you can only have one password. So the total outcomes we have to now add, and that's the additive principle that we have. Now, I've kind of made this a little even more, you know, what would have happened if the characters are only numbers, right? Like what if we restricted it and it was only numbers? So in this case, you know, you can probably see that all of this that we just did, I'm going to kind of erase this out so that we have space here. So if I remove this and I say, okay, if they're only now numbers, so this is B instead of A, well, then that means how many numbers? So in terms of numbers, okay, let's assume that they mean digits right here. Okay, so that's each character is a digit, I guess not a number. Okay, so it's a digit. So, well, the digits that I have that are possible are 0, 1, 2, and so on, all the way up to 9, if they're just 1. So that's 10 of possible choices. So again, what I would have to do is, with 3, okay, I have 10 possible choices for each one, right? So for each of them, assuming that they can be repeated. Now, if they can't be repeated, you know, then you would have to do something else. You would have to subtract in some way. So now this, well, clearly you can see this is just 1,000. So a lot less than we had in part A. Now, if we had 4, so that would have been 1 possible choice, 2 possible choices, right? And all of them are 10. I'm going to start writing them in, so what this is just 10 to the 4. And then for the 5, well, you get the gist, this is to the 5. And now what do? We got to add all of them up. So this is 10 to the 5 plus 10 to the 4 plus 10 to the 3. So that is the additive principle, but to compute each individual one, we use the multiplicative principle for counting. And from that, you know, we can go ahead and do this. This actually isn't that bad because of the fact that it's all tens. We don't technically need, you know, to punch it all out in a calculator for ourselves. So here it is, right? You can see all the ones because the 5, the 4, and the 3 in terms of the exponents. So this certainly makes sense. 1, 1, 1, 0, 0, 0. It's only 111,000. Remember, the other one was like 387 million possibilities. Now, of course, okay, if you would do, how about if all the characters are numbers or letters? Haha. Okay, if they're numbers or letters, well, we just said, so in terms of letters, if they're small and capital, so that's 52 possibilities. Plus the numbers, that's an additional 10, right? So for each one, now all of a sudden, we have 62 possibilities. So now, if that was the case, and I would redo all of this, okay, let me remove that, or at least maybe let me shrink it. Okay, maybe I should have done that with the other one. So for that, you know, if we did, so part C, now we have 62 possibilities. And from that 62 possibilities, well, you can see that a password, so made out of 3, okay, now it's 62, 62, 62, right? So you get the idea. This would have been cubed. To the 4, I don't even know if we're going to be able to punch this into the calculator, but we'll see. This is going to be to the 4. And with 5 characters, a password, right, would have been that. And now, so if we add them up, 62 to the, okay, we'll see what it gives us, plus 62 to the 4, and plus 62 to the 5. Wow, it's quite impressive. So almost a billion, right? So it's 931,147,496. Crazy, okay, the number of possibilities. And this is how we can use, okay, and we can count all of these different things up, right? So that's another example that you can see, okay, these. And clearly the mutually exclusive, where things can't happen at the same time. Having a password with 3 and then having another one, you can only have one password out of all of those. So this is a really nice example. Here is a last example that I have for you, because, you know, through computers, they really just send out zeros and ones. All of this, okay? It can figure out from zeros and ones all these wonderful colors. You know, you're watching YouTube and videos, right, from all of that. So now in this digital world, let's say, okay, and it asks a question. How many words can be made if a max of 8 digits can be used, right? Notice, so what happens is, okay, so now it's 8 digits. We pass a lot more than that. 8 digits, by the way, created of zeros and ones, it's called a byte. Maybe you've heard of that, right? So byte, okay, is 8 digits. Now here it says a maximum. So, you know, we can send 1, we can send 2, we can send 3, 4, 5, and so on. So notice, once again, we're going to have this mutually exclusive idea happening. So if you have, for instance, that if you can send out, so stage 1, you can either send out a 0 or you can send out a 1. So really, these are just 2 outcomes, right? 2 outcomes, that's it. And that would have made sense because I only have a 0 or a 1. So there's only 2 possibilities that I could have. Now, if I would, so stage 2, if I was going to send out 2, right? So the word would be made up of 2 digits, either 0 or a 1. So, I mean, we can still do this, right? So it could be a 0 and a 0. It could be a 0 or a 1. It could be a 1 and a 0, and then a 1 and a 1. Now, of course, we don't want to continue this trend in finding these outcomes. It didn't ask us for the outcomes. It just said how many possible ones we had. So in this case, we had 4 possible outcomes. Now, instead, again, just use the multiplicative. So I can have either a 0 or a 1. So I have 2 possibilities. That's why it's called binary, if you've ever heard of that, okay, in terms of the digital world. And then I have another possibility. Notice if I multiply them, then this is going to give me 4. Right? Now for 3, so now I'm going to stop doing this. Okay, so I know that this is going to be 2 possibilities, 2 possibilities, 2 possibilities. So either 0 or a 1, 0 or a 1, 0 or a 1. And now in this case, so this is 2 to the 3, so 2 cubed, which is 8. And of course, could have done that. So now the next one, which is going to have 4, you get the trend. This is going to be 2 to the 4, right? So this is going to be 16 possibilities. Now, to the 5, right? So this is now 2, okay, to the 5. And this is going to be 32 possibilities. And notice that they're going to start growing on us. 2 to the 6, this is 64 possibilities. 2 to the 7, all right? This is 2 to the 7. Is 128. And then with 8, so which is 2 to the 8, which is going to be 256. And now what do we do? If you want to know the total number of possible outcomes, right? So if you're going to be sending out a word, if the word is only 1, kind of 0 or a 1, there's only 2. If it's going to have 2, it's going to have 4 outcomes. And all we do now is we just add all of them up, which is the additive counting principle. I'm not going to do that. You can add it yourself. But I hope that this gives you a gauge of seeing that if things are mutually exclusive, that they can't happen simultaneously, you can do each individual stage and then just add them all up. All right? Okay, so thanks for watching, and I'm sure we're going to be seeing you in a lot more videos. Okay? Cheers, everybody. Bye. Take care.